Here we go. So the title is Kondo destruction, dynamical Planckian scaling, loss of quasiparticles. And I cannot move with the pointer, so let me do this. And so let me start by thanking at least some of the collaborators, Hao-Yu Hu, Lai Ching, and Tsai from Rice University, some continued collaboration with Jed Pixley from Rutgers, and with Kevin Ingersoll and his student Anand Candela, have a continued collaboration with Stefan Kirschner. We have a lot of interactions with the Silka Passions group, and in particular also her student, Lucas Prochaska. And I'll mention some work done recently with my colleague, Dag Nathanson, and his student, Li Yang Chen. And over the years, I've had a lot of interactions with a number of distinguished experimental groups, Frank Staglish, Joe Thompson, Hubert von Loneisen included. So coiled electrons, I just want to sort of set the stage. We have genetic problems of some bands of electrons, some genetic interactions, U, band with W. And when interaction is weak, we learned in the textbooks how to do perturbation theory. Physically, we're considering when we treat interactions perturbatively for these interacting electron systems, we are making the premise that conduction electrons are the building blocks for the physics that we look at. And of course, there are phonons as well. What happens when interactions become large, meaning that the strength of the interaction reaching the bandwidth or exceeding that, one could continue to treat the problem with the conduction electrons alone, together with phonons as the building blocks, but it's also becomes meaningful. And sometimes it's very useful to treat some effective degrees freedom, such as local moments as the building blocks for the low energy physics. So perhaps the most canonical setting for this is the heavy fermion metals, in which the F electrons experience a strong Coulomb repulsion, so much so that typically local moments are the effective degrees freedoms if we want to understand the low energy physics. And it's also very convenient in the sense that there's a separation of energy scales which are generated that would not have been there if one thinks in terms of purely electrons. And so these are some recent articles which give some basic material, some status report on this in this general area. What the focus of this talk is about is primarily on quantum criticality. So this is a genetic phase diagram in the cases when there's a order, that long-range order that's promoted by some parts of the interactions of the system, and a disorder that's promoted by different terms in the Hamiltonian, and one can tune some control parameter to go through a quantum phase transition, and there are cases where it's essentially continuous, so we can talk about quantum critical point that influences strongly the regime at extended parameter regime at non-zero temperatures. And there's some good and relatively simple reasons to think that this regime is interesting for unusual excitations and emerging phases. One could do back of envelope dimensional analysis to make a statement that the physical entropy is accumulating in the vicinity of the quantum critical point, and which goes along with the notion that the system would be extremely collective. So so some time ago with Achim Roche and Li Junzhu, Marcos Gas, we just did a very simple thing, which is to ask the question, what if you look at the normalized free critical component of the normalized free energy, how should it behave as a control parameter? R measures the distance from of the control parameter from the quantum critical point, so that R is tuning this axis, and then the quantum critical point, which is a singular, can also be reached along the temperature axis. And if it were thermally induced phase transitions, tuning this way and tuning that way for genetic critical point, there's no difference as far as the singularities are concerned. But for quantum critical point, there is, and the details are not very important. The spatial dimensionality, dynamic exponent, the correlation length exponent are new. And so this would form the combination that scales according to dimension of the normalized free energy. And this tells us how temperature scales with the control parameter. So you can rewrite in a number of different ways, leading to the statement that actually I don't have a plot here, but to show that the entropy as a function of, if you stay at a very low temperature, scan through the isothermal tuning, you'll find that the entropy is maximized in the immediate vicinity of the quantum critical point. And that's actually can be measured. For instance, this is the effort made by the Karlsruhe group, in which they measured a certain thermodynamic quantity, basically how the volume or how the length changes with temperature. And you can use Maxwell relation to construct the entropy landscape. And indeed, one finds that the vicinity of quantum critical point is sort of at the top of a mountain as far as the entropy landscape is concerned. So if it's if there is the entropy accumulation, this is a regime where the system is amplified, in this case, quantum fluctuations, and the system is very soft and is prone to developing, reorganizing the low energy excitations, and maybe even in such a way that nucleating interesting phases, perhaps also high temperature superconductivity. Now, to the further level of specifics of the nature of the quantum critical point, the traditional framework starts from the Landau theory of phase transitions already for thermally induced phase transitions that at low temperatures, one has a broken, spontaneously broken global symmetry, and the quantity that characterizes a spontaneous broken global symmetry is the order parameter, such as stagnant magnetization, anti-ferromagnet, and the criticality would be described by the fluctuations of the order parameter. So that's well established for thermally induced critical points. For quantum critical points, that has also been formulated, going with a long history, and perhaps the modern era started with the Chakrabarty helping Nelson on the Heisenberg magnet in 2 dimensions. My cursor, let's see. Oh, here, it's back. Okay. Now, focusing on the quantum critical metals, this actually, the history is actually longer than what I just mentioned about the magnets, going back to the work of John Hertz, continuing with the work of Millis and others for finite temperatures. And one could think of it as the singularities captured, quantum critical singularities captured by the order parameter fluctuations, and with well-defined fermions coupled to the singular order parameter fluctuations. And in cases which are of pertinence to the kind of systems I will cover in this talk, it would have been a spin density wave, a order of the spin channel at some non-zero ordering wave vector. And so in fact, these well-defined electrons keep their integrity for the most part of the Fermi surface, because most part of Fermi surface would not be connected by the antiferro, the order parameter wave vector to another fermion excitation at the low energies. And so in a picture like this, there should be a lot of quasiparticles which are still around at the quantum critical point. And so there's a lot of interest in looking for quantum critical points in metallic systems where the quasiparticles are completely lost. And that question also gets connected with the question about criticality. Can there be, for quantum critical points, can there be critical modes that go beyond the order parameter fluctuations? So I'm going to narrow down to these Kondo lattice systems, where again, picture the F electrons which interact so strongly with each other that they act at low energies of our interest as the localized moments. So this term would describe the usual quantum magnetism, have a band of itinerant electrons. So we can, for the practical purpose, we even just consider as non-interacting electrons. And symmetry allows these two species to be coupled in terms of spin-spin interactions, and for good reasons, it's typically antiferromagnetic. And so that we have the degrees freedoms, the building blocks, we have the conduction electrons, we have the spins. Of course, we could also put other things like fermions into the mix. And so if we want to talk about the ground states, we know what the fermions would be doing alone, reaching a zero temperature limit, but the spins, we have to ask what's the fate of local moments. And as by way of background in this field, the typical starting point would be that the local moment are entangled with the spins of the conduction electrons. So in the process, they became swallowed by the spins of the conduction electrons. They don't order. And so this would be represented by the singlet between these localized spins, these black solid arrows, forming singlets with the spins of these mobile conduction electrons, these red smaller arrows. And so that's a ground state. And the electron excitation spectrum has been described for a long time in terms of the conduction electron bands, the dashed line here, the dispersion, mixing with, if you wish, a flat band coming from the Kondo effect, forming these hybridized bands, which you can represent in terms of the dispersion or in terms of the density of states with large peaks near the Fermi energy. Everything is happening near the Fermi energy within a scale of some bare Kondo scale. And this KF and the KF star will become clearer if we wait for a few slides. And so this comes out from some particular calculational schemes, but physically you could understand these flat composite fermions forming hybridization with the conduction electrons by making the analogy with say a BCS superconductor, where we have Cooper pairs in the ground state, and then we can think about the Bogoliubov-Djian quasiparticles by breaking up these bound states. Here we have a bound state of the spin of local moment and spin of the conduction electrons, which is a particle-hole combination. If you want to break that apart, you can break apart, knock an electron out. That would be a bare electron. That's the dashed line in the dispersion in the previous slide. But you can also be left with this composite object, which is spin one half combination. So you can end up with spin 1/2 and it's a charge E object. So from quantum numbers, it behaves basically as a fermion, but it's a very heavy object. And these objects exist only because in the ground state, we have formed these Kondo signal. And so that's a picture that describes, these are a number of different ways to think about the Kondo singlet ground state. But of course, we have the competition between the Kondo effect and the quantum magnetism. So the fate of local moments doesn't have to be unique. There's could be forming a singlet between the local moment and the conduction electron spins, but there's also a lot of quantum magnetism that would be allowed in the ground state. So one could expect that this is a rich phase diagram. And so let me talk first about some aspects of quantum criticality, which incorporates the interplay between the Kondo effect and the magnetism of the RKKY interaction. The simplest case would be the antiferromagnetic order that's caused by the RKKY interactions between the localized moments. And so when the RKKY interaction dominates, we have in this case consider it's the antiferromagnetic order. When the Kondo term dominates, we have the Kondo singlet in the ground state, and the Landau type of quantum critical point would only have the fluctuations of the antiferromagnetic order parameter. And but if one considers these Kondo singlet formation with some particular amplitude measured by a scale, which I'm going to call the E local star, if that the strength of a Kondo singlet goes to zero, this scale would also collapse to zero at a quantum critical point, and then we have the fluctuations of the magnetic order parameter and the fluctuations of these Kondo singlet. Everything happens under the protection of the bare Kondo scale, which is a smooth quantity and non-critical. But in the ground states, we have this competition of the RKKY and the Kondo singlet formation. So I'll describe just very briefly the approach we've taken, and in a few slides I'll come to why historically this question was motivated based on some dynamics properties of these quantum critical points. When all this got started, it was only primarily one experiment, so most theorists didn't take it very seriously. People like Piers Coleman, Catherine Papin, myself, and some others decided to take it seriously. So happened that we've been developing some extended version of DMFT, which diagrammatically you can look at the single particle Green's functions capturing these diagrams and the RKKY interactions that are intersite. And this it's not a random summation of the diagrams. There's some effective action potential that underlies the equations for this, which comes out as a saddle points. But pictorially, one treats a Kondo lattice model and asks what's the fate of local moment, and the local moment effectively couples to the fermion bars, as in the usual case of the Kondo problems, but also coupling to the bosonic bars coming from the quantum fluctuations. If you start from the paramagnet side, the quantum fluctuations of the local moment that comes in as an effective bosonic bar. So the local problem, which is going to be treated self-consistently, that will describe the spin dynamics and other collective properties, as well as the single particle states, which is the Bose-Fermi Kondo model, pictorial represented here. And so this problem can be treated using some epsilon expansion RG calculations. And so there's the Kondo coupling, which is a direction which, as usual, if Kondo singlet formation is captured by the flow of the Kondo coupling towards strong coupling. And then depending on the power of the exponent of the bosonic bath, I'm going to represent it as omega to the power of 1 minus epsilon. So when epsilon equal to 0, it's a genetic case, like a particle hole excitation from a metal. But when epsilon is positive, the coupling to the bosonic bath is strong enough to compete with the coupling of local moments to the fermion bath. So it ends up that there's a critical point separating the part of phase diagram which flows towards the Kondo fixed point to the part of the phase diagram where the Kondo effect is completely, there's a fixed point which is completely destroyed. And so one could already at this level of the both Fermi, Kondo, or Anderson models, one could understand why there's a loss of quasiparticles. Because if one is on the left of this red separatrix, the system flows towards the Kondo fixed point. So depending on how close the starting point is, the Bayer problem is to the separatrix, the energy scale, the effective, eventually that comes into this E local star. The low energy definition of the Kondo scale will be relatively large if the parameters of the problems here become smaller and smaller, progressively smaller as I approach the separatrix in any of the directions. And that strength of the Kondo singlet formation, describing how far does it take to flow towards strong coupling, measures the weight. Let me just go back. The weight of this composite fermion. So let's call that a Z. So Z is non-zero if I'm on the left of a separatrix, and the Z becomes smaller and smaller as I approach the separatrix, and Z vanishes when I reach that point. And so that's already one way to see that in some sense, even if for one-band Hubbard model, you can think of quasiparticles strongly in the bad metal regime as coming from collectively through some effective Kondo effect. Here it's actually a real Kondo effect that's generating the quasiparticles. So if I destroy this mechanism that generates the quasiparticles, I destroy the quasiparticles entirely, right? And so one could do better for a model like this by actually looking at the finite size spectrum, which in a recent piece of work done with Kevin Ingersoll, the primary calculation of his student, and then Candela, we can look at a spectrum. And when for fixed Kondo coupling, scan G across the red, the separatrix. If I'm on the left, the energy levels flow in a particular type of spectrum. If I'm on the right, it flows at another distribution. So if I'm on the left, when G is larger than GC, I'm going to the Kondo destroyed fixed point. When G is less than GC, I'm flowing to the Kondo fixed point. So here, where these levels are flowing to, eventually I can understand the low energy part of the finite size spectrum in terms of Fermi liquid description with the quantum numbers are such that it's arranged according to a quasi-particle description. And the level spacing, you can introduce phase shift to parameterize them. But if I stay on this critical value GC, meaning crossing the separatrix, I end up with a spectrum which up to iteration number 41 here, it's distributing some particular way. And there's no way one can use a Fermi liquid description to quasi-particles to understand this spectrum. So we know that there's a complete loss of quasi-particles for a critical point like this. Precisely how to actually parameterize this spectrum is a harder question, but I know that Fermi liquid has been lost. Yes, P.S. Yeah, sure, absolutely. Yeah.
Does this quantum critical point have a 0-point entropy like the multi-channel Kondo problem?
So and any epsilon, yeah, absolutely. So at any epsilon from 0 to 1, there yes.
Yes.
But the self-consistent solution in the end is the epsilon going to 1 minus. Mm-hmm. That's where this residual entropy goes away.
Okay. Thank you.
Yeah. That's a good question. So so that's it's in the sense that there's a well-defined way to understand that the quasi-particles are lost. Now, in addition, this is an interacting fixed point. It's not a Gaussian fixed point. And so if it's an interacting fixed point, dimensional analysis should work. And one of the consequence of that is that KBT is the only energy scale in the problem. So if I measure dynamical quantities, such as finite frequency response, h bar omega is going to scale with KBT. And so this is perhaps a more general way of thinking about quantum scaling with h bar in it. We might as well call it Planckian, dynamical Planckian scaling. And so for this problem, usually one does the calculations in imaginary time, analytic continuation, etc., becomes harder. But from this finite size spectrum from the numerical RG, one can also calculate the real frequency response. And you can see that over many decades of omega, in particular h bar omega over KBT, there's a collapse of the, in this case, the spin susceptibility. Eventually it deviates. So if say temperature is 10 to minus 4, when omega reaches on the order of 10 to the 4, all these in units of the Bayer-Kondo scale, you can see that you've reached this this dividing line T0, and so everything one goes out of the scaling regime. But below this scale, the curves get onto the universal part of curve, and the same statement can be made at different temperatures. So this drop here reflects the going out of the scaling regime at higher energies, but at the low energies at the critical point, one follows this universal h bar omega over KBT scaling. So now we want to study a lattice problem. So I actually don't really want to go through these equations unless there are questions, but it's basically this picture formulated in describing the equations, treat the Anderson model as supposed to be Kondo model, but it's the same if you use much larger than V. And so this is the fermion part describing local moment coupled to the fermion path. This is the imaginary time representation of the local moment coupled to the bosonic path, and will allow the possibility of long-range order. And so again, like effective action like this can be constructed as a saddle point of some potential, or at least the equations associated with this, and with the self-consistency in the spin and single particle and the order part self-consistency constructed. And so one of the first things that motivated this line of work was to see whether there's h bar omega over KBT scaling in the spin dynamics at a quantum critical point at the antiferromagnetic wave vector. If one follows the Landau scheme, because the dynamic exponent z is larger than 1, d plus z, the effective dimensionality is above the upper critical dimension, and one expects violations of the naive dimensional analysis. But once one incorporates this Kondo destruction physics, the critical point becomes interacting instead of Gaussian, and h bar omega KBT scaling is restored. And as already said, that's because KBT is the only energy scale in the problem. There was a particular motivation to look at Q away from the antiferromagnetic wave vector as well. And so one can just generalize, it turns out in this analysis, one can generalize this equation to Q away from capital Q. And we made an effort to use different kinds of numerical methods to calculate this exponent, and it came out to be about somewhere around 0.75. That was important because, as I alluded to earlier, one of the initial motivators was the experiment by Gabe Apley, Elmer Schroeder, Hilbert von Neising, Pierce played a very important role in analyzing this data that provided motivation for this line of work. Over in the data over about 4 decades of h bar omega over kBt, one sees this scaling collapse with a exponent that's fractional of near 0.75, and the fact that one could also look at the Q away from antiferromagnetic wave vector to get this portion out in the analysis. But perhaps at least for us, the guiding principle was, first of all, can we get h bar omega over kBt scaling, and secondly, does the exponent did the exponent come out reasonably? And so that was the reason for this big effort, what we consider to be big effort through different kind of numerical calculations. Now, more recently, so this calculation was actually done for the Ising spin anisotropy, just because of more practical, in part because it's more practical, makes the calculation more practical, but in part also because this system is actually has a strong Ising anisotropy in the spin response. We've recently looked at the SU2 symmetry case of this Boas-Fermi Kondo / Anderson model, and turned out that the fixed points were much richer. And so this was the work of An Cai, who actually developed this SU2 version of some continuous time quantum Monte Carlo method for studying this sort of problem, reaching enough of temperatures. We were I should actually add that reference. There was a indication for this critical point by forgot his name, Tsuki, I think, a 2013 work, which showed that instead of the 1/tau to the epsilon behavior, it's a constant in tau correlator. So it means that instead of 1/t to the 1 minus epsilon local spin response, it turns out to be Curie 1/t, and I didn't believe it. So we looked at this problem in some detail, and to our surprise, at the epsilon expansion for the SU2 problem, when epsilon is small, there's not only this fixed point that's accessible by the epsilon expansion, but there are 2 more fixed points. And in particular, this one is a stable fixed point that has a different correlator. And so we studied the overall flow of the RG, and showed it turns out that there's a new Kondo destruction critical fixed point, but unlike between here and there, between here and there, the correlator is the same, and that's actually very important because that's the only way for the self-consistent problem to have a solution. And there's a more recent understanding based on some general phenomena of fixed point annihilation. There's a very nice paper by Adam Nahum written here. We also have some work that's unpublished, but describing how, and that was numerically, we actually showed that this is when epsilon is close to 0, S is close to 1, but when epsilon becomes larger and larger, eventually this fixed point, which was very dear to some of us, actually completely go away. So this pair of fixed points annihilate, and left with this alone when S it becomes smaller than some S star, meaning epsilon is larger than 1 minus S star. And so this is for we also this prompted us to actually reanalyze the phase diagram. Pierce, please.
Given the sensitivity of the fixed point diagram, just going from anisotropic to isotropic, what do you think about how sensitive it will be against the inclusion of finite dimensionality and going beyond the EDMFT?
So we do what we can, right? So even at the EDMFT level, that fixed point structure concerned me, and so do we still find the Kondo destruction within the EDMFT, right? And And if I may, let me describe that, and then we can have a general discussion of what to do beyond what can be calculated at the present time. And there's some hints, the kind of things you are doing, we are thinking about different parts of the overall phase diagram. And I think would be a good discussion, right? So we made an effort to use this SU2 method to analyze a phase diagram. And there's always two types of solutions, but the important thing is what I call type 1 solution. And I'll describe what is the input for that still exists. Namely, this E local star, which is the scale. You can say this is infrared definition of the Kondo scale. It still collapses to 0 at the antiferromagnetic quantum critical point. And then we can calculate the dynamical response. This was done in imaginary time. So, but the omega of the t, h bar omega of the KBT scaling still operates at this quantum critical point. So in the SU2 problem, there's a behavior in spite of the complexity of the surprising complexity of the fixed point structure that we still have a Kondo destruction critical point with the loss of the quasiparticles through this E star scale collapsing to 0, and dynamical h bar KBT scaling. Now, we also looked at, I haven't told you what type 1, type 2 analysis in the model calculation is actually what the input is. So the input for the type 1 solution is you allow what I call the distribution of the RKKY interaction I sub ij, the Q space, and form a denser states to have a jump at the edge. That's when the type 1 solution happens. If it goes to 0, in particular, say in a square root fashion, would ultimately this E local star at the critical point would be non-zero. So this would be a way to get going back to the Landau description of the STW quantum critical point. So we actually never looked at this problem until recently. And it turns out that the scale, meaning that this infrared Kondo scale could be non-zero at the quantum critical point. The scale turns out to be always very small. And let me just first give you a sense of the scale measured in terms of bare Kondo scale. T0, remember, is the cutoff at high energies. It's always at the level of 5% or so and below. And so that's important. For instance, the typical systems like say silicon copper to silicon 2 is considered to be a canonical case in this category. A Kondo temperature would be 20 Kelvin. So we're talking about the crossover scale, which is on the order of 1 Kelvin. And I'll not describe the experiments today, but in connection with superconductivity on Wednesday, I'll mention the indications for that. But so what do we? So this kappa is just the measure of how far from the lower edge that goes in the square root portion as opposed to be the constant portion. So there's a good reason for that. The spin density wave itself would be formed by these F-based composite fermions. And so you first have to establish at the onset of these F quasiparticles at the TK0 scale. And then once you have the well-defined heavy quasiparticles, then they can form spin density wave order, right? So there's a hierarchy of a scale. And so even the energy scale, the transition temperature into the spin density wave order, such as in silicon copper to silicon 2, would be small when you measure it in terms of the bare Kondo scale. It's further amplified by the competition between the dynamical competition between the Kondo singular formation and the tendency of the quantum fluctuations associated with the associated with the RKKY interactions. So in practice, even in the cases when the asymptotic low temperature, low energy behavior is controlled by this Landau type of quantum critical point, there's always a large dynamical range over which the quantum critical behavior is controlled by these destruction of this crossover scale being zero physics. And that's actually something that in looking at the superconductivity, I will come back to. It's a very important aspect. What kind of dynamical fluctuation is driving pairing? Okay, so I want to go on to go beyond the dynamical scaling of the collective responses to the single particle physics. And so the statement that follows, in addition to having these unusual exponent in the dynamics, is that there is the Kondo singlet formation in the ground state in the parallel magnetic case, in the type 1 case, directly transitioning into the anti-ferromagnetic order. So here, the ground state supports these well-defined quasiparticles, and that makes the Fermi surface to be large. When the Kondo effect is destroyed, the ground state is such that it does not support these well-defined composite fermions in the excitation spectrum, and the Fermi surface becomes small. So the question was whether that can be tested. And so unlikely inelastic neutron scattering data, this aspect actually at the time had not been probed. And so how do we, let me just say a few more words about this Fermi surface change. So I already mentioned from say the finite size spectrum, or just from general considerations of quasi-particle weight, that if there is the Kondo destruction, then the quasi-particles would be lost at the quantum critical point. Now, before the quasi-particles are completely lost, you have the non-zero, this infrared Kondo scale that describes the finite spectral weight of the quasi-particles, which you can capture by a pole in the energy space of the conduction electron self-energy. So the suppression of the Kondo scale can be considered as suppression of the strength of this pole. And when you have this pole, you get this hybridized band picture qualitatively, and that's how the large Fermi surface formation is accomplished. But if you destroy the strength of this pole, you go back to the Fermi surface that's formed by the conduction electrons alone. So the along with what goes hand in hand with the complete loss of quasi-particles at the quantum critical point is that there should be a large to small Fermi surface transformation in an abrupt way across the quantum critical point, even though it's a second order quantum phase transition. And so this, let me just summarize some of the fairly well-known experiments by now. One is in ytterbium rhodium to silicon 2. There's a field-induced quantum critical point where the nail line collapses. And in fact, there's also good indication that the Fermi liquid scale collapses, which would be this ELO. This goes with the complete destruction of the quasi-particles. But the transport measurement, the isothermal Hall measurement, where there were checks that's measured in the normal Hall response, so it's connected to the Fermi surface features. The isothermal Hall effect shows a very rapid crossover as marked by these curves, and normalizing some particular way, and over 1.5 decades of temperature, this width of the crossover extrapolates to zero. So extrapolates to a zero temperature jump. And so two things which are both interesting and in a good sense important. One is that there is a rapid crossover, the scale T star, that's decoupled from the long range magnetic orderly. So that says that this piece of physics is not associated with the long range order, which gaps out the Fermi surface, as was established, for example, in the chromium case, as a function of either doping or as a function of pressure for giving doping. And the other is that the width of this crossover extrapolates to zero that there's a jump. Again, that's also in contrast to the well-established spin density wave quantum critical point, such as observed in chromium. And so the terbium rhodium to silicon to I want to highlight it because I want to come back to it about the nature of the quasi-particles or absence of it at a quantum critical point, which is specified by this quantum critical fan as giving T star would be right cutting through the quantum critical fan. In some cases, such as in cerium rhodium indium 5, where there's a pressure-induced quantum critical point around 2.3 GPa, it's convenient. So it's anti-ferromagnetic to paramagnetic. The system is amenable to quantum oscillation measurements, and so these are the frequencies that came out of the quantum oscillation measurement, and one does see that across the second order quantum phase transition, magnetic paramagnetic quantum phase transition across PC, that there's a sudden jump of the oscillation frequencies. And not all of these branches, but many of these branches have been identified with the Fermi surfaces of the small Fermi surface, where you assign F to be completely localized. And some of these branches are identified with the those of the itinerant F electrons. And the effective mass shows a tendency of divergence. In some sense, it must happen, otherwise it cannot be a second order phase transition. So that would be compatible with this quasi-particle rate going to zero when the system is approached, when a quantum critical point is approached from both sides. Now, what about directly, what happens at the quantum critical point? In addition to scanning across the quantum critical point, observing the large to small Fermi surface changes, can one directly probe the statement that there are no quasi-particles at the quantum critical point? So, in this context, we Doug Natelson's group, who has the expertise of measuring shot noise using the film made the MBE films of the terbium rhodium to silicon 2 made in Vienna, and they patterned it into these wires of these typical length scales, slightly below 1 micron scale, and this allows Doug's lab to measure the noise, and noise is something that has been thought about a lot in certain communities. I think the correlated electron community probably it deserves to be further considered more extensively. But there's some calibration, some markers when we start to think about this problem. So one is that if you have well-defined quasi-particles, if disorder scattering dominates, picture shown here, there's some well-defined calculations one can do, such as based on random matrices. There's a statement about what the short noise should be for such a diffusive metal. If you stay with the well-defined quasi-particles, but the electron scattering dominates the scattering as opposed to the quenched impurities, there's a slightly different picture, basically because you open up one way to think about it, you open up the energy window and for the fluctuations. And so the markers are that if it's well-defined quasi-particles with disorder scattering dominating, it would be 1/3. And so the experiment was done using simple metals, these wires of gold, and indeed it's approaching the 1/3 of that in this experiment. If you consider well-defined quasi-particles, but electron scattering dominates, it turns out to be square root of 3/4, again, one could think in terms of opening up the energy window for fluctuation, for this out of equilibrium fluctuations, and that turns out to be larger. Now, imagine that the extreme version of the complete loss of quasiparticles. Not only that there are no quasiparticles, but there are no dispersive features in a single particle spectrum at all. In which case, it's like you lost the discreteness of the current carriers. So one would expect that the noise would be very small. So all these, sorry, I said 1/3 square root of 3/4. That's based on this Fano factor. So there's a complicated expression at the non-zero temperatures, but the simplest is just to consider short noise limit when the drive is larger than the KBT. And in that case, you can just parameterize, normalize the noise by the current, and that defines this Fano factor. So that's the basis for this 1/3 square root of 3/4. So the experimental measured value in this quantum critical fan region from 10 Kelvin to about 3 Kelvin is telling us that indeed this Fano factor is much suppressed, and it doesn't seem to be marching towards the 1/3 value within the experimental uncertainty. So it's closer to this complete loss of a quasiparticle, the complete loss of dispersive features than to the 1/3, although of course, I mean, even in the cook plates in a strange metal regime, if you do RPS, you still see dispersive peaks in EDC and MDC, energy dispersion curves and the momentum dispersion. Yeah.
So to do this measurement, is it a point contact measurement, or do you need a wire?
It's a wire, so I think I had a geometry.
It has to be 3D like, or do you actually study a truly 1D system?
So the transverse dimension, I mean, it's not that small, right? It's not a 1D limit. So you could think of still in a 3D case. The films are not in a single layer limit either. And the width certainly is not, I don't think they can pattern to the atomic scale. So that gives you a scale. This is the 1 micron, and that's the wire.
So it's a 3D system, more or less.
Yeah.
Just very spatially.
Yeah.
Yeah. And therefore, all of these predictions, there are some predictions for this 3D geometry.
Yes. But I don't think there's a distinct, if I have a diffusive metal with what?
It's truly 1D, it's like
Yeah, no, so that's definitely not. There's nothing that's non-firm liquid in those statements about 1/3 and the square root of 3/4. Yeah. So far, around 10 years ago, there were also some measurement on the Wiedemann-Franz law or violation of it, and there was reasonable extrapolations which about 10% violation of Wiedemann-Franz law in the zero temperature limit, even though that statement was disputed, but I think the analysis is quite reasonable. But so I think the short noise adds to this probe of the loss of quasiparticles. It also raises interesting theoretical questions in different regime of the correlated systems, core electron systems. How do we think about noise? And we've been thinking a bit along this direction. How much time do I have, Pearson? We're already in the discussion time. Maybe I can finish, take a few more minutes, and then leave some parts for Wednesday anyway, right? Continuation. So I do want to, I already mentioned type 1, type 2, which is sort of like in the trees, I suppose, the forest. But we've thought about how to put the type 1 transitions and type 2 transitions. Type 1 is the Kondo destruction, complete loss of quasiparticles coinciding with the magnetic transition. Type 2 would have the asymptotic low energy behavior is SDW. So I want to emphasize, so we came with a new subscript of R standing for anomalous quasiparticles. I'll see how people like it or don't like it. But nonetheless, the physics is real, that anything that's controlling the Landau type of quantum criticality, it only happens at much lower energy scales compared to the bare Kondo scale. And there are other regions that one can study, which I'm not going to. So there's some frustrated spin systems one could study. One could imagine generalizing this EDMFT type of calculations with clusters of different kinds. Or you can take really frustrated spin systems as a starting point and a couple of fermions into it, the kind of things that Pierce and his collaborators are working on in the recent time. But I want to mention some aspects of the materials effort, because just like this, you can go to, this is G is a frustration characterizing the quantum magnetism. JK is the Doniak axis of the Kondo versus RKKY competition. And one could look at it, one could start from this corner, for instance, and start with nonlinear signal model description of the spin system and put in fermions. So just like different parts of the phase diagram lend themselves to different kind of calculation, and then the large Yang mean field calculations. In some cases, like Shastri Southern lattice, you can cover these different parts of the parameter space. I want to give some sense that there's a large materials effort, which is connected with these theoretical considerations of global phase diagram. So one thing that was done in Vienna with Silke Pashin's group was that there's some materials which are cubic, and the G should be small, so should be realized this portion of the phase diagram. And there's some evidence that that's indeed the case. Large G case, you want to think in terms of very naturally various kind of geometrically frustrated lattices that you put the Kondo lattice in. So for instance, there's some FCC by Paul Canfield's group and some Kagame, especially these 1-1-1 systems, which actually continue to be of extensive interest. The cerium, palladium, aluminum is what I want to, let me just in the next slide, I want to say something about the cerium, palladium, aluminum, which is a quasi-Kagame. But even in this good old cerium 115 systems, there's efforts of looking at the different, whether it's rhodium or rhodium-iridium combination and the cobalt, and put some effort of maybe based on these orbitals that vary from one type of 115 system to the other as the means of tuning across the different parts of phase diagram. And that, in some sense, that's a very interesting question. How do we invent tunings that could connect with these parameters? As of now, most of these is just to say, I'm tuning as a function of pressure, doping, magnetic field, and must be a scan in this direction, except for this 3D being here and geometrically frustrated lattice being there. And so maybe this is, let me just mention, because I think there's some interest in this kind of systems. Cerium, palladium, aluminum is a quasi-Kagame lattice. There was a lot of work in Karlsruhe about 10 years ago. And the past couple of years, there's two groups, a Beijing group and also the Augsburg group, have probed the pressure tuning of this system in combination with the magnetic field tuning. And lo and behold, in addition to the magnetic transitions, there's a range of non-ferromagnetic liquid-like features based on transport measurement that was uncovered. And there's a recent magnetic measurement of USR and I think neutron scattering as well, which seems to indicate some interesting spin responses in this range, in this extended range. And we quantitatively consider the pressure tuning and the magnetic field tuning through the global phase diagram allows us to interpret this in this way, but obviously microscopic analysis would be theoretically microscopic analysis would be very informative to see whether in principle in this Kagame case such a phase can really be done. So I think actually the charge response part very naturally connects with the superconductivity that I want to talk about on Wednesday. So I mean, I'm happy to continue, but maybe it's more meaningful if there's some discussions already now.
Good. for discussion, questions from the audience.
Thank you.
So you showed us, basically, you talked about properties of electronic spectral functions, spin susceptibility. Can we use your theory to compute things like non-local conductivity, signal phenomena?
Yeah, so conductivity is much harder in this set of calculations, but one could make a genetic statement, but one would like to do calculations that there's a contrast with the SDW quantum critical point. In the SDW quantum critical point, I said the non-zero capital Q is only connecting the hot spots on the Fermi surface. So much of the Fermi surface is cold. And so in fact, much of the Fermi surface, the scattering rate would be Fermi liquid form. So you have a T square, so they will dominate the contribution to the current. And so in the end, asymptotically, you should see the Fermi liquid transport. While if the entire Fermi surface, the quasiparticles are lost, you would expect non-Fermi liquid form, and to the extent the scattering rate satisfies this naive dimensional analysis, you would expect the scattering rate to be linear in temperature. And that way of thinking actually provides, so you're asking a theoretical question, but let me answer in a way that I think it's an interesting, it's an interesting observation that the materials I mentioned, like terbium, rhodium 2, silicon 2, cesium, copper 6, gold, cesium, rhodium, indium 5, etc., that shows this from either spin response or some other responses that shows indications of a complete loss of quasiparticles. Those are the ones which actually give you T-linear resistivity empirical. While the ones which have such as cerium, the famous one being cerium, palladium to silicon to pressure tuned quantum critical point. We don't know a whole lot about the properties near the critical pressure, but the resistivity, say, has a T to the 1.2, and some may have somewhere with exponent that is somewhere between 1 and 1.5, and maybe even larger exponent. So that the calculation by Ahi Roche, which you start from this cold spots, hot spots model, and put disorder in principle, you could have apparent exponents of this.
About which temperatures can you see this phenomenal scaling?
So for instance, T-linear resistivity. There's a recent work by the Vienna group, by Silke Pascher's group, which has gone down all the way to several millikelvins. Maybe John also has data. And so T-linear resistivity is observed in non-doped, the residual resistivity is like 1. To be fair, that's an experiment that's done in the with a small amount of magnetic field, but I don't think that changes residual resistivity. These are extremely clean systems. The residual resistivity is like 1 micro-ohm centimeter scale, and yet you see T-linear resistivity going all the way from 10 Kelvin or so to several, like 3 millikelvin, so like 3.5 decades of temperature. So it really seems like the asymptotic. It's going all the way to like upper cutoff, which is some fraction of the T0 scale I mentioned, all the way down to the for electron systems, the really close to zero temperature. So that's harder, but it has been, so in fact, I don't know, maybe I can show, I actually don't, so I'll promise on Wednesday, but you may not be here, but there's you can look at the optical conductivity at low temperatures. Low temperature actually here means 1.4 Kelvin. It's a terahertz measurement, so it's much more limited. And you can ask, what's the inverse of the optical conductivity, terahertz optical conductivity? How does it go with frequency? And come out to be linear in frequency, but it's much harder to get 3 decades of just you run out frequency window in the upper limit, and you run out of frequency window at the lower limit in terms of the techniques that's available to measure. But within this new measured range, this is the omega of a T-scaling collapse of the terahertz conductivity that I'm showing.
Other questions? Yes.
Yeah, please.
Okay, so I've seen some indication that people have tried to generalize quasiparticles to deal with more strongly entangled systems. The one thing that I was curious about was maybe for the problems, classic problems, you can consider sort of like a full picture that is really like the appropriate basis, say, to write a Hamiltonian thing if you're
Yeah.
strong.
Yeah.
Like, can you think about like a quanta of entanglement or something like that?
Or even at the more physical excitation level, if there are no single electron lambda quasiparticles, are there some other quasiparticles? You know, some maybe fractionalized quantum numbers or some other things. So we know examples such as two-channel Kondo case where you destroy the single particle lambda quasiparticles, but you actually have a hidden Majorana fermion as the elementary excitations. So I think these are the kind of problems that provide the opportunity to address the questions that I think you're raising. We're not there yet, but.
Did you say there's a basis that people are working with already where like the object that that you write the Hamiltonian with is like fundamentally like non-local?
So for instance, I think what you're asking is that suppose that we have 1D interacting fermion problem. So the quasiparticles are completely lost. But if you go to a different basis, bosonize it or otherwise, you actually have elementary excitations that exist, right? So that provides proof of principle a case, quantum critical from all the physical responses perspective, whether a model like this that I've talked about at the quantum critical point, whether there's a elementary excitation that exists, it's a question we looked at to some extent in this impurity models. In some cases, the finite size spectrum can actually be rationalized by some other elementary excitations. But for this case, we don't know the answer. But it's with enough information, or maybe even some variations of the models, maybe one can get to that point. But it's a good question.
The RG equation, the RG graph became a lot more complicated for SU2.
Yeah.
Have you tried looking at SUN for higher end? Is that a bit too?
It's so we actually yeah. So you can do. It turns out that this fixed point annihilation picture that I talked to you about. So why would this epsilon expansion fail to capture these additional fixed points, but capture these two fixed points? Because these two fixed points for epsilon small, meaning the power omega to 1 minus epsilon is close to 1. We have these fixed points which are within the reach of that epsilon expansion. But turns out that these 4 fixed points, they cannot be captured. And the reason is that epsilon expansion is based on an expansion which is the analog of a high temperature expansion of the phi-4 theory. And so this fixed point, these two fixed points, for instance, can be captured by using a different starting point, which is the analog of the nonlinear sigma model, the low temperature expansion. And but you need some additional parameters to access it. So it turns out 1 over S is easier. So analytically, one could imagine, maybe more than 1 over S. There's some other 1 over N's to go with 1 over S in such a way that they keep track of things. So it's very new. I mean, when we had the numerics, it took me a long time really to believe it. But I think we're gradually gaining some insight. So SUN would be very interesting. Just to establish, say SU3, what's the analog of this? And some of these can actually be realized by cold-atom simulators. So maybe these fixed points can be actually probed directly. Yes.
Question. So I should probably stop at
Yeah.
1 o'clock.
John also had a question. But yeah.
So taking the table realities for consideration, some, I mean, the use of Fermi systems, the Fermi surface is pretty complicated.
You mean a real Fermi surface,
Real Fermi
as opposed to my model
I
Fermi
mean,
surface?
so
Yes.
you measured, but there are calculations by people like Sweden.
Yes, correct.
And as you go over the Fermi surface, the effective mass varies hugely as you go over that.
Yeah.
So you're talking about as I understand it, the complete loss of quasiparticles over the entire Fermi surface. So how do you reconcile those two things? There's sort of a heterogeneity.
Yeah. So there's no question that different portions of this very complex spider-like Fermi surface would have different amount of scattering rate. The question is whether each point on this complex Fermi surface in the quantum critical region has T-linear scattering rate or not. As you know, in the cuprates, actually now there's a progress, even though it's simpler Fermi surface, but one actually has information now that the scattering rate, there's a T-linear part everywhere on the Fermi surface. There could be some constant background which varies in K. And so the real question is whether, in spite of the difference in the amplitude of a scattering rate, whether everybody is hot in the sense, or there are some bystanders. And it's empirically, I think it's very hard to imagine there are bystanders, because if there are bystanders for such a clean system, 1 micro-ohm centimeter residual resistivity system, by the time you reach 10 millikelvin, they should dominate the contribution to the current. And one doesn't see that. I mean, I think that's really amazing aspect of this new Vienna experiment, that go all the way down to your temperature range. And so I believe that there are no T-square portion of the Fermi surface. Whether one could imagine doing something like what the cuprates community are getting out of it or not, I don't know.
When you cross the Néel transition ceremony in that system,
Yeah.
you get T-square.
Correct.
So what's your understanding of that? Is the local moment, the order moment is incredibly small.
Yeah, but nonetheless, in the phase diagram, you are to the left of the quantum critical point. So it cannot, the criticality cannot persist all the way down to the low temperature. There must be a cutoff scale. And in fact, it's a success story that cutoff scale is systematically mapped out already by transport. And maybe, we want more measurements to map out that crossover scale. But I think it's a fully consistent. Yes, you did have a question.
Well, I did. This is
To raise it for discussion.
Let me just point out one thing
Yeah.
that the Planckian community loves to duck and cover from, which is the fact that there's a very well-defined T-squared cotangent of the Bohr angle in quite a few strange metal systems. This means that the scattering rate associated with the Hall effect naively is not the same as the one that's associated with the linear transport.
Yeah.
And first of all, if you have T-squared, that means there's a scale.
Mhm.
Okay. Second of all, it poses a major problem to the understanding that there's as you mentioned, there's a T-linear seen all the way around the Fermi surface.
Yeah.
So where's the T-squared coming from? And what's this scale? I think it's obviously not just an issue of Planckian dissipation in these systems. And it's very nice, and we're here later this week, that the SYK models give linear and other things. But to all of these locally based systems, I asked the question, where is the T-squared scattering rate?
Yeah. I mean, the boring answer would be that T-linear part is the leading scaling
No, 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 no.
component.
If you're
You
multiplicative
could have
effect,
subleading, but
Take X,
I
Y is
prefaced it.
multiplicatively a product of two.
yeah. So what? But
scattering
why
rates.
would it be that the transverse scattering rates pro by Hall would only be picking up T square and not the leading
That's part of the
T?
question.
Yeah. So I agree with you. It's a
It should be
it's a very universal question. That's seeing T square Hall angle is seen in these quantum critical heavy fermions, certainly seen in the cool plates, and maybe even in the.
And on that,
yeah.
it's good to end with a question. Thank you all coming. Thank you, Qimiao. And let us go for lunch. Some of us will go to the Goddess of Life Greek restaurant, where we've got 10 reservation for 10 people downstairs. Hope you join us. See you all at 2:30
2:30
this afternoon.